cart of mass lowercase m is 0.2 kilograms moves on a horizontal air track with velocity at moment 1 equal to 0.5 meter per second. It collides elastically with a second cart, capital M is 0.3 kilograms, initially at rest. Compute the initial kinetic energy of the system, find the final velocities of lowercase and uppercase m, and finally, if the collision occurs in 0.1 seconds, what is the average force exerted by car 1 on car 2? This problem differs from some of the other collision problems because it is defined to be an elastic collision. Collisions can be categorized by the amount of energy that they do or do not conserve. All collisions conserve momentum since there are no external forces acting on the objects during the collision. However, depending upon the nature of the force between the two objects, they may or may not conserve energy. Whether and to what extent energy is conserved sets a condition on the final state of the two objects after the collision. As we know, any time there is a collision, at the moment before the collision, the two objects are approaching one another. After the collision, they may or may not be receding from one another. The principle that allows us to identify an elastic collision is that the speed at which they recede from one another after the collision is exactly the same as the speed at which they approached one another before the collision. If the collision is partly inelastic, then the speed at which they recede from one another is less than the speed of the approach. And if the collision is totally inelastic, we can recognize that one very easily because the objects do not recede from one another, but instead they stick together, representing the collision that dissipates the maximum amount of energy. In this problem, we're dealing with an elastic collision. And so for that reason, we know that, number one, momentum is conserved, as it is in every collision. And number two, since the collision is elastic, energy is also conserved. For the problem at hand, it is a one-dimensional collision leading to one momentum equation, one energy equation, and therefore it is a problem with two unknowns. However, if we were to set this problem up using one momentum equation and one energy equation, we would find that the algebra is somewhat difficult. The reason is that the energy equation with 1/2 mv squared will give us quadratic equations to deal with, and that will make the algebra much more difficult. Since we know we need two equations, we recognize that we in fact have three possibilities. The third possibility for an equation is given in the hint. This third possibility reflects the principle that we discussed previously about an elastic collision. And that is, for an elastic collision in one dimension, the speed with which the two particles recede from one another after the collision equals the speed with which they approached one another before the collision. Looking carefully at the formula, we see lowercase minus uppercase v, both at moment 1, that is the speed of approach, and we see lowercase v minus uppercase v at moment 2. That is the speed of receding. The minus sign in the formula simply reflects that prior to the collision at moment 1 they approach, and after the collision they recede. Since this problem requires two equations for its solution, and there are three available, the most intelligent route for us is to choose the two equations that yield the simplest algebra in achieving our solution. And these two equations will be the momentum equation and the principle of velocities equation, because these two both have velocity to the first power and will wind up being very easy to solve algebraically. Before we proceed with the momentum calculation necessary for part B, let's take a moment to solve part A and get that one out of the way. In part A, we are asked to compute the initial kinetic energy of the system, and that will be the sum of all kinetic energies of all objects, which will be lowercase m times its velocity at moment 1 squared plus 1/2 capital M times its velocity at moment 1 squared. As usual, I am using numerals to denote which moment. So velocity at moment 1 is always subscript 1, and I am using capitalization to denote which object. So we have lowercase m with lowercase v and uppercase M with uppercase v. Since the large mass is stationary at the original moment, its term gives us 0, and the total energy in the initial moment will simply be 1/2 0.2 kilograms times 0.5 meter per second squared, which is equal to 0.025 joules, or 25 millijoules. Now let's move on to that collision. Momentum is intrinsically a vector quantity, and therefore, just as with forces, we get one equation for each relevant dimension in the problem. This collision is one-dimensional, and so we only get one momentum equation, and that momentum equation looks like this. Here, as always, lowercase refers to the smaller object, and uppercase refers to the bigger object. The numerical subscripts refer to moment 1 and moment 2, and this is our conservation of momentum law written out in its entirety. We couple this law with the principle of the velocities. Since we know the masses of both objects and we know the velocity of the smaller object at moment 1, we can fill those in, leaving us with two equations in two unknowns. These are now two equations with only two unknowns, and we can solve these by solving one of the two equations for one of the unknowns, plugging that into the other equation, and proceeding with the algebra. Since the second of these two equations is simpler, I'll solve that one for lowercase v2. This result can be plugged into the first equation, thereby eliminating lowercase v2, leaving us with an equation only in uppercase v2. Collecting the terms for uppercase v2, we can then solve for uppercase v2, yielding 0.4 meter per second. This result can be plugged into any of the prior two equations. I'll pick the simplest one, which is this one here, so that I can rapidly solve for lowercase v2, which is equal to negative 0.1 meter per second. Let's take just a moment to think about these results. This is the case of a moving object hitting a stationary object. For an elastic collision in which the two masses would be the same, after the collision the moving object is stopped and the stationary object is moving away with the same velocity as the original incoming moving object. However, if the incoming mass is larger, both objects will recede, moving in the original direction, but when the incoming mass is smaller, the incoming mass will bounce backwards. Looking at our result, we see exactly this character, because the heavier, previously stationary mass does move to the right at 0.4 meter per second. However, the lighter mass recedes from the collision in the opposite direction to which it came in, having a velocity of negative 0.1 meter per second. Finally, in the last part of the problem, we're asked to calculate the average force that either one of the carts applies to the other one, or by Newton's third law of equal and opposite, receives from the other one. In order to solve this, we turn to the formula that tells us that the impulse, in many textbooks this is given by J, and in all textbooks it is the force times a time interval, equals the change in momentum. At this point, this may seem like a rather bizarre application. In the previous part of the problem, we decided that the system conserves momentum, so that the total momentum in moment 1 was the same as the total momentum at moment 2, because there are no external forces, and therefore the change in momentum was 0. Here we are about to calculate a change in momentum that is not 0 in order to derive a force. How can this be? The answer to this very good question depends upon how we have defined our system. Clearly, when the two objects collide, cart 2 applies a force to cart 1. Cart 1 applies a force to cart 2. These forces are equal and opposite, meaning that the total impulse to the total system, consisting of both cart 1 and cart 2, is 0, and the total system does not change its momentum. However, if we isolate either of the carts, then we see that cart 1 experiences a force from cart 2 and changes its momentum because of it. Cart 2 experiences an equal and opposite force from cart 1 and also changes its momentum. Therefore, in order to solve this using the time interval of 0.1 second, we can either consider the change in momentum of cart 2, or we consider the change in momentum of cart 1. Cart 2 is somewhat simpler since its initial momentum was 0. Therefore, the force we are looking for times a time interval of 0.1 seconds is going to be equal to the after momentum of cart 2 minus the initial momentum of 0, yielding 1.2 newtons. Notice that if we had actually done the alternative calculation for cart 1, we get the result negative 1.2 newtons, equal and opposite to the force applied to cart 2.